So lastly, we'll put it all together to solve a linear programming problem using this simplex method. So here we need to do the full procedure. So we start with the linear programming problem. This is in standard form, so we don't have to worry about rearranging anything. But we do need to set up the initial simplex tableau, and then we'll need to pivot until we're done with the negative indicators, and then we can read off the final solution. So here, remember that to start with, we would need to take these two constraint inequalities and turn them into equations. And we also want to rearrange this initial equation, which is the objective function equation, so that we just have that constant on the right side and all of our variables on the left side. Now, if you're comfortable with doing these steps mentally, then that's fine. Notice that because there are two constraints, we would have two slack variables, S1 and S2, and then we have the optional Z column, and then the constant column over here. So if you're comfortable just introducing the slack variables mentally and rearranging mentally, then what we should get is a 1, a -5, a 1, 0, 0, 25 for that first row. Your second row would be 4, -3, 0, 1, 0, 12. And then your objective row would be a -4, a -6, 0, 0, 1, 0. So if you're comfortable just immediately writing that down, then that's fine. You can also take the time to rewrite these initial equations. So this is what you would get from rearranging the objective row. This is what you would get if you added that first slack variable to the first inequality to turn it into an equation. And this is what you would get for that second constraint equation. So if you need to write down the corresponding system that we get after doing all of this rearrangement and introduction of the slack variables, that's fine, but you can skip this step if you can immediately write down the initial simplex tableau. But either way, what we should end up getting is this initial simplex tableau. Now we know that this is not going to give us the optimal solution because there are still some negative indicators here. So remember that what we should do is we should go through this procedure to find the pivot, and then we will, once we have the pivot, we'll go through the pivoting process until either we're unable to continue doing the pivoting process or we have gotten rid of all of the negative indicators. So let's look here at the pivoting process. So remember, you start by identifying the most negative indicator. That will tell you which column the pivot lives in. And then the second step in pivoting tells you to look for any of the positive entries in this column and compute those quotients. But notice here that there are no positive entries in the column. So what this means is that we will be unable to select a pivot. So here there is no pivot. And what this means in terms of the problem is that there is no way to maximize Z. So this is one of those weird things that happens just like in systems of equations. We could have dependent systems or inconsistent systems. This is sort of the edge case for the simplex method. So if you start looking for a pivot and you can't follow the pivot rules to select a pivot, in this case we can't find a positive value to serve as the pivot, then what we know is that the initial linear programming problem actually has no best solution. So there is no way to maximize Z. So the conclusion here is just that there is no optimal solution. And you're completely done with the problem at this stage. So if I ask you to solve the linear programming problem and you make it to a point where you can't follow the pivot rules to select a pivot, then you can just stop and say no optimal solution. However, be very careful that you are following the pivot rules correctly here, because I think a lot of people are tempted to sort of short circuit the problems and say that there is no optimal solution when in fact there is, and you'll lose a lot of points that way because you're missing a lot of the work for the problem if you get something like this wrong. So be very careful whenever you say that there is no optimal solution, but what I would do for this procedure is just keep the pivot rules in front of you, and then if you see that you're unable to select a pivot, then that means that there is no optimal solution for that linear programming problem. What this means is just that you can get arbitrarily high values for z within this within this set of constraints. So there is no best value for z. You can always do a little bit better than any particular z value. Okay, so that's the answer for that one. That's the last example that's going to be covered in section 7.4. There is one more example that I've added to this set of notes, but this problem comes from section 7.5, so that's what we'll talk about later in the week. So I'm not going to work through this problem today. This will be the first problem that we look at next time. But I did want to show you what an application problem might look like for linear programming. So here you have an office manager that has some constraints. They have some cabinets that cost $40 each but require 6 square feet of floor space, and they hold 8 cubic feet of files. There's another type of cabinet that costs $80 each. They require 8 square feet of floor space, but they hold 12 cubic feet of files. We have some budget constraints and some storage space constraints, and we want to maximize the number of files that we can store. And the question becomes, how many of each type of cabinet should we buy given the constraints on our budget and the constraint on the amount of square footage of floor space that we have? So this is an example where you have this word problem, but you can translate this word problem into a corresponding linear programming problem. So here we know what we're trying to optimize. We're trying to optimize the amount of storage space that we have, right? So we want greatest storage capacity. So Z is going to represent storage capacity. And here the question is, how many of each type of cabinet should we buy? So I would maybe call these ACE cabinets X1. So X1 will be the number of ACE cabinets. And then there's also the Excello cabinet. X2 might represent the number of Excello cabinets that we should buy. So we have that we're trying to optimize storage, but we also have some constraints. We'll have a constraint from the square footage of floor space. And we'll also have a constraint from the budget. So this will be the first thing that we talk about next time, but if you'd like just to sort of practice, you can try translating this already into the corresponding linear program, and then you can try to solve that linear program on your own. So you have all of the tools that you need in order to do this, so this would be a good opportunity to practice using your word problem skills and also to sort of solidify the stuff from this lecture. The linear program for this problem is on this next page. So if you want to check your answer, you can just scroll to page 11 here, and it has the linear program for this problem. But we'll also talk about setting this up next time.